Okay, so welcome back to our discussion on test of hypothesis. And this session, I'm going to talk about tests concerning two populations. Once I'm done, I'll talk about tests concerning more than two populations. Now here, you see, we have two populations, and then we are interested in the average, okay, of these two populations. We want to compare them. Are they the same? Is one greater than the other or less than the other? That's the test we want to do. Now, so the first thing is this. If you want to test this, you need a null hypothesis. So the null hypothesis here will be that you have population 1, its mean is mu1. You have population 2, its mean is mu2. So H naught is that mu1 minus mu2 is equal to a particular value. It may be 0, D naught may be 0. If it is 0, then what it means is that the populations are equal. Okay. However, I can also test whether the differences between the population 1 and population 2 is equal to, let's say, 5 or greater than 5 or something of that sort. Okay, so it's not always the case that your D naught will be 0. Okay. All right. Now, so you state your null hypothesis. The alternative hypothesis, if it is one tail, then we may be interested in checking whether the alternative mu1 minus mu2 is greater than, D naught, or mu1 minus mu2 is less than D naught. But if it is two-tailed, then we want to test that mu1 minus mu2 is what? Not equal to D naught. Okay. Now, so let me just scroll down and just look at this example just to illustrate. So for example, here you have two meat 1 and meat 2, okay, products, and then we are checking the fat content. So meat 1, you have maybe this is beef, and the other one may be chicken, and then this one you have 30, 26, 30, and so forth. The next one you have this. So the idea is to check whether the meat products have the same, do the meat have different fat contents, right? Okay, so here, because you want to check whether they are the same, then I'll be interested in checking whether mu1 is equal to mu2 or it is not equal to. So that's how you state your null and alternative hypothesis. So you see here, the null hypothesis is that mu1 minus mu2 is equal to 0, as against mu1 minus mu2 not equal to 0. So that's what I mean by the two-tailed test. Okay. Now, what is our test statistic? Is because this is small sample. If it is small sample, we are assuming that our the sample we took from population 1 and that of population 2 are less than 30, right? Each of them is less than 30. Other than that, we can consider them as being large samples. If it is large sample, then we are not going to get this T, but rather we will assume that it follows the normal distribution Z, the standard normal. So it's just like the other one we did. Okay, so mu1 minus mu2 is the D naught, okay, which is about the population. So this is a pivot, which is, it has a function, it's a function defined on the D naught, when D naught is on mu1 minus mu2, so it's a population parameter, but this distribution is completely known. Okay, now S is the sample standard deviation. So it's assumed that we don't know the standard deviation of the population. Okay, and here we are assuming that they are we pull them together. So this is a pooled variance, right? If they are different, then it means we are going to get S1 in here and then S2 squared in there. Okay, so that we can pull them together. So if they are close to each other, we can have a pooled variance, which is S. If they are not close, we just say X1 and S2, right? And for population 1 and or sample 1 and then sample 2. Okay, so if it's a pooled variance, this is how you get your pooled variance. If not, it means you have X1 which is the sample x1 squared, which will be the sample variance for sample 1, and then s2 squared, which will be the sample variance for sample 2, and then you put them as the together as a standard error. Like you divide this by the standard error of what? X1 bar minus S2 bar. Okay. Your rejection region, just like the one sample test, we can have greater than, which is like that, and then less than, which is like that. If it is 2 till, then we reject for large values and also for smaller values. Okay. Now, what is our degrees of freedom or the critical values? We can read from T. So if it is 1 till, we are dealing with T alpha. If it is 2 till, then we have our T alpha on 2. And our degrees of freedom is what? N1 plus N2 minus 2. Okay, so this you can read from any tables once you have what? N1 and N2, which are the sample sizes for the samples you took from population 1 and population 2 respectively. Okay. Now, so here, if we check here, our sample sizes are 10 each, but of course you can have the two samples may have different sample sizes. So please note that it's not always the case that you will have the same sample sizes, so it can be different. Okay, so this is one aspect of this test of hypothesis, which is that here we can call it two sample independent t-test. Okay, so here I'm assuming that I'm taking some samples from two different populations. Now, another one that I'll talk about is a paired sample to t-test. Okay, so the example we took over here, we had two meat companies, or let's say two meat products. So they are different. The chicken and beef, they have nothing in common. Like they are not the same. Okay. Now there's another test where we talk about differences between paired. Okay, paired difference. What do we mean by paired difference? This is where you have examples like this. So look at this one. You see, you have participants, and then they are being weighed before and after a program, just like our Norwegia data in R that we've been using. So you see the participant, we are taking two samples from each participant before and after. So here, when we want to consider them, it's like before is like a population and this is like a population, right? So that's why we say two samples. But actually, the observations are on the same participant, right? Before and after. So the test we do is on the differences between the in this case weight before and after. Okay, so if you look at the sample test, because we have computed the differences and this is considered as one sample. So that is what we mean by paired sample test. Okay, so here, what is our null hypothesis? Our null hypothesis is what mu d, and mu d is the difference between mu1 and mu2, which mu d is just the differences. Okay, so for the average of the differences. The alternative hypothesis, just like the one tail test, and the test statistics is d hat, and d hat is what the average from our sample for the d's. Okay, the differences, and sd like that. Okay. And our critical region, just like the one tail test for one sample and two tail test for two samples. Okay, here the critical value also for one tail is T alpha, but please look at it. The degrees of freedom is n minus 1 sample test, because our test is on the differences between the means. Okay, so please note these two. These are the two different test we can do concerning the two samples. Okay, so now that I have explained the basis for this, I'll now go to R, and then we will start with our practice on these two tests. Okay, so we now come to R, and then we want to do our test concerning the two samples The first one we will talk about is the independent populations. Okay, so still we're going to use our t-test, right? The t-test, but now we will have x and y. Our alternatives, we will have mu, okay? Paired will remain false because this is independent test. Now, one more thing I will look out for is var.equal, whether it should be false or not. Okay. So the example we're going to use here is on the CAS 93 data, right? Now, so for CAS 93, remember we did talk about the drivetrain. So I have here the levels of the drivetrain. And if you look at it, we have 4W, the front and then rear wheels, okay, the drivetrain. Now, what I want to do is simply this. I want us to check to test a hypothesis concerning the price of the cars, right? But we want to check whether the price of the cars for front wheel drives is different from that of rear wheel drive. Okay. Now, so I'll start first by getting the prices of cars which are front wheel. Okay. So you see this selection, I start first by saying what is cars.price. Of course, this will give me all the prices of cars, and there are 93 of them. Okay. However, I want to select only cars with front wheel. Okay, so this is a vector. So I just input in my condition, which is cars with drivetrain equal to. And you see I have equal to. So with front wheel, which is front. Okay, so because I know the levels to be 4WD, so I want those with front. And please, your spelling must be right. Other than that, you won't get it. So once I run this, I have my front wheel prices. Okay, so which is the data we're going to use. Okay, so the next thing is that we want those with rear wheel. If we want those with rear wheel, I'm going to change this to rear W. Okay, and then here instead of front, I need what? Rear. So I come here, I copy rear, and then I change this to rear, and then I run this too. Okay, so this also gives me rear. Remember now, if I want to know my sample sizes of the data, look, length of front view is 67. So we have 67 front views. Now, if I also check for rear view, you see that's 16. Okay, so that's what I was saying, when, that we may test a hypothesis concerning two populations, but the sample sizes may not necessarily be the same. Okay, so that's about it. Okay, for that comment. Okay, now, okay, so let me make a comment here. Okay, so test hypothesis. The price of cars. The price of cars according to their drivetrain. Okay, according to their drivetrain. And in this case, we want to test a hypothesis concerning front view, and what? Rear view. So the test is to check whether the price of rear view drivetrain is significantly different from that of front wheel. Okay. Now, so one more thing. The sample sizes are different, but remember that in our t-test, as I said, so X will be front wheel, Y is rear wheel. Alternative, we are going to do two-sided, so we will say not equal to. Mu, we will maintain it to be 0 because we want to check whether they are the same or not. Paired, we know will be false because these are two different samples. You cannot have a car that is front wheel and at the same time it is rear wheel. We have combination of them, but you cannot you cannot be solely front wheel and then solely a rear wheel at the same time. That's what I mean. Now there's an argument var dot equal is equal. So by default it is false. If it is false, it means that the two populations have different different variances. Okay. Now this, you can't just say that they are, if you compute the variances and they are not equal, you cannot say in statistics you must test, right, a hypothesis to be able to conclude that the variances are not equal or they are equal. Okay. All right. So before we do our test, we will check or we will test for equality or variance. So we test for equality or variance for the two populations. For the two populations. In this case, front and what? Front and rear drivetrains. Okay. Now, so how do you do this test? Or how do you conduct this test? There's a var.test. Okay, so this is also a hypothesis test, and the help file of var.test is this. So it's a f-test to compare two variances. So I have two populations. I'm going to test whether they are the same, right? The variances are the same. Now, because this is variance, it's ratio of two variances. So if the ratio is equal to 1, it means the populations, the variances are the same. Okay, because the numerator and the denominator will be the same. If not, then it means they are not the same. So that's how I'm going to conduct this test. Okay, so basically I'll use the default two-sided and the variance confidence level also 95. Okay, so I copy this and I'll just use the X and Y. All the rest are default. Okay, so the result of my test, var.test, X is rear, Y is front wheel, and then we have this. Okay. Now, how do I interpret my result? So it's what? F-test to compare two variances. Data, rear wheel, front wheel. My computed F is this. Degrees of freedom for the numerator is this, denominator is that. The p-value is this. Now, if I'm using the p-value, I can say that I will reject my null hypothesis. Why? Because the p-value is smaller than my than the level of significance. The level of significance here is of 0.05. So if my p-value is less than the level of significance, I reject my null hypothesis. Now, one other way is that we can also compute the critical value for the F, and then we compare this F with it. How do I compute my critical value? I will say QF, okay, my P is equal to 0.05. Lower the tail is true, so okay. So I can say 0.95, okay. The DF1 is what? It's 15. DF2 is equal to what? 66. Okay. And I can leave the rest like that. So I run this and I get 1.82. So if you look at my computed F is greater than what I read from the tables. Now for F test, you only reject for large values. So we reject the null hypothesis. Now, one other way is to also use the 95% confidence interval. Okay, so the interval is 1.36 to 6.91. Now, remember that if our population variances are the same, then the ratio will be equal to 1. So the ratio of our variances, the interval does not include that. So it means I do what? I reject it. So it's not what? Equal. So what it means is that now I have a basis to now go to my t-test, and then I can change var.equal is equal to what? False. So I'll maintain it. If we had not rejected the null hypothesis, in other words, if the variances are the same, then I would have done var.equal is equal to false. So here I will leave what? This equal. And the confidence level, maybe we can take it at 0.95. So we are good to go for our test. So now we can conduct our test. Okay. We have so X, we said X was a rear view, so I can put it here. X is rear view, Y is front view. Okay, so Y is front view. Alternative, I think for now we say we are doing two-sided. Okay, so I'll delete everything with the exception of what? Two-sided. Okay. Then mu will leave it at 0 because we said we want to test whether they are equal to 0. Paired is false. Okay, so I leave it like that. var.equal, we've seen that we must choose that to be what? False. They are not equal. And then confidence level is 0.95. So we leave it like that. Okay, so we are good to go, or we can now conduct our test. Okay. So let me see. We are now going to test. Okay, so our comment is that test for equality of prices for rear and front drivetrains. Okay, so there we now conduct our test. Okay, now so I look at the results. Now look at it. You see, when the variances are not equal, I'll use what is called Welch two-sample t-test. But if the variances are equal, it will use the normal t. Okay, which is the pooled variance. Okay. Now, so look at it. This is a result. Welch two-sample t-test. Okay. Now, so the data we have rear view, front view. Our test statistics t is equal to 3.53. The degrees of freedom, remember this one, it has decimals. So this is not the n1 plus n2 minus 2, but this is computed as and that's why computed as some with a formula, and that's why we have 17.66. The p-value is small compared to 0.005. We will reject the null hypothesis. In other words, there are differences between what the two prices, or the average prices for rear and front wheel drives. Okay. Now, so alternative hypothesis, we say two differences, it means is not equal to 0. Let's look at our 95% confidence interval as a way of deciding whether to reject or not to reject our null hypothesis. Remember, if our null hypothesis is true, then the differences between the averages will be 0. Now look at it. Our confidence interval between the two, right, is 4.25 to 18. This does not include 0, or it doesn't include 0. So what do? We reject our null hypothesis. Now the test also give us the sample estimate. The mean for the x is 28.95. The mean for y is 17.53. So the conclusion for this test is that the prices, okay, of the rear wheel drives and that of the front wheel drives are significantly different. In other words, the averages of the the car prices are completely different or significantly different. Okay, so next we look at paired samples. Remember, we said paired samples are where you have units and then you take two samples from each unit. Okay, so here we're going to look at the anorexia data. Okay, and to get anorexia, you should have uploaded your mass package. Okay, so let's display it and see. We know about this, or if you like, we can go to the health files and look at the paired the data on anorexia. Okay, so it's what? A data frame of 72 rows, 3 columns, weight change data for what? Young female anorexia patient. Okay, so but I'm interested here in the weight. So there is weight of patient before the study period, and then post weight, which is what? Weight of patient after the study period. So we want to compare these two ways too. And if we display the data, we will see that you have paired weight. So the first person received is in the control group. The pre-weight is 80. The post-weight is 80.2. So the person reduced in weight, okay, but quite marginal. The next person too, there was a reduction. The next person, there was a reduction. The next person, there was an increase in the person's weight before and after the program. Okay, so our interest here is to check whether the pre-weight and that of post-weight are significantly different. Okay, for this test, you want them to eat and then to gain weight, right? So our interest is not a two-tailed test, but what we want to know is that your pre-weight should be less than what? Your post-weight. So this will be a one-tailed test. And this one-tailed test, we are interested in what? That the meal one should be less than what? Meal two, right? Where meal one is the pre-weight, average of the pre-weight, and meal two is the average for the post-weight. Okay. So we're going to copy the same test, okay? But remember, sorry, the same test. But before we do that, we must also check whether our var dot equal what should be our results. So we need to check for the variances to check to see whether the variances before and after the variances between the weight of the anorexia patients are significantly different or not. So anorexia, and then I do the dollar sign, I choose pre-weight, and then anorexia, and then I take post-weight. Okay, so first of all, so this is test for the this is like a success of the weight program. Weight program in the anorexia data with the anorexia data in mass package or package mass. the mass in the mass package. Okay, and we've seen anorexia. Also here, we say check for equality of variances. Equality of variance. So we are checking for equality of variance. Okay, so let's see. Okay, so this is our results. Okay. So if we look at the F, the p-value is very small. So what do? We will reject the null hypothesis. Look at this one. The confidence interval for the ratio does not include 1. So still we reject the null hypothesis. Okay. So what it means is that the variances between the two are not equal. In other words, we side with the alternative hypothesis, which is true variances is not equal to 1. Okay. All right. So that's a quick one. And we can make a comment that since the variances are not equal from the test, we set var dot equal to what? False. Okay. In other words, what do? You maintain the default. Okay, the default selection. So var dot equal is false. Okay. Let me change X and Y. So I copy and I paste. Okay. So we have our data, anorexia pre-weight, anorexia post-weight. Alternative, here the alternative is what? We want pre-weight to be what? Less than what? Post-weight. So this is less. Okay. Okay. Mean 0, that's fine. Paired here should be true because this is paired sample. But var dot equal, that's what we found over here. We set it to false. Confidence level, we maintain it at 0.95. So let's see. Okay. So there it is. This is the results of our test. So see the results of our test. It says is what? Pair t-test. Data is anorexia pre-weight, anorexia post-weight. Our test statistics is a T, remember, and it's negative 2.93. So what it means, even the test statistics will tell you that the pre-weight is what? Less than the post-weight. However, we don't know whether it is statistically significant. That's what we are about to do. So if you look at the p-value is small. So what do? We can reject the null hypothesis, which is equality of the variances. Okay. So the true difference in means is less than 0. Okay. So what if you look at the 95% confidence interval for the difference in mean, it does not include 0. So we can say that it's actually negative. And then the sample means of the difference is also negative. Okay. So what is our conclusion for this test? The conclusion is that the post-weight, the average weight for after the program is significantly larger than that of the before the program. Okay. So in other words, the weight loss program is or leads to what? An improvement, significant improvement in the weight of the participant. Okay, so that's how you conclude this test. So up to here, what we have done is that we have considered a one sample test. We have also seen a two sample test. And the two sample test, we have independent test and also paired test. And please know that for the two-sample test, before you start your test, you must always check to see whether the variances are the same or not, so that you will be in a position to choose the required um, argument for the or the answer for the argument var dot equal, which is logical, whether it is false or true. So that will be our discussion on one and two sample test. Okay, so lastly, you consider this assignment, and please, everybody should take part in this. Okay, so do this and let's discuss them on our platform. If you are facing any problem, do let me know. Okay. Thank you. So the first one, you want to test at a significant level of 10% whether the CBT treatment is better than family treatment. Better here means what? There's an increase, significant increase in weight. And then also the B part, you are to test at a significant level of 2% whether CBT treatment leads to what? A significant increase in weight of patient. Okay, thank you.